Every day, millions of people step into metal boxes, sit down, and trust their lives to a transportation system most of them don't understand. They assume someone else figured it out. They assume it just works. They never look deeper. But inside every train car, there's a hidden world of mechanical precision that would make aerospace engineers take notes. Systems within systems, backups for the backups, engineering solutions that took decades to perfect. If you're someone who actually wants to understand how the machines around you really work, this is for you. Because trains aren't just transportation. They're rolling masterpieces of engineering. What you're looking at when a passenger train rolls into the station isn't just a vehicle. It's an engineering marvel operating on a scale that defies common understanding. A single passenger car weighs between 40 and 60 tons empty. To put that in perspective, that's equivalent to stacking 8 to 12 full-sized SUVs on top of each other. And that's just one car. A typical passenger train might have 8 to 12 of these cars linked together. The propulsion systems on modern high-speed trains generate up to 9,000 horsepower. That's more than a Formula One car, a fighter jet engine, and a freight truck combined. This immense power isn't just for speed. It's necessary to overcome the physics of moving hundreds of tons of steel with precision. Inside each train car, the electrical systems consume enough power to run 50 average homes simultaneously. From the climate control systems to the lighting, from the door mechanisms to the onboard computers, these machines are effectively small power plants on wheels. Most remarkable is the operational schedule. These massive machines operate 18 to 20 hours per day, covering distances equivalent to crossing entire continents, with precision measured in seconds. By any common sense standard, something this complex should break down constantly. And yet modern trains achieve 99.9% reliability rates. To appreciate the engineering marvel of today's trains, we need to understand where they began. In 1825, the first passenger railway carried 450 people at 15 miles per hour, and that was considered a miracle of speed. Those early train cars were essentially horse-drawn carriages bolted to wheels, with no suspension, no heating, and absolutely no safety systems. Passengers were expected to endure bone-jarring rides, freezing temperatures, and the constant threat of derailment or boiler explosions. The first real breakthrough came in the 1860s, when engineers finally realized that trains needed to be designed as integrated systems, not just carriages placed on tracks. This shift in thinking led to the development of proper suspension systems, safer boilers, and the first primitive braking systems. By 1900, luxury trains like the Orient Express featured electric lighting, steam heating, and dining cars, technology that wouldn't reach most homes for decades. These trains weren't just transportation anymore. They were showcases of what engineering could accomplish when pushed to its limits. After that, progress accelerated. Air conditioning in the 1930s allowed passengers to travel in comfort through deserts and tropical regions. The transition to diesel-electric power in the 1940s eliminated the need for water stops and increased operational reliability. And the introduction of computer control systems in the 1980s revolutionized safety and efficiency. Despite 2 centuries of innovation, the core principle of train engineering has never changed. Trains are about managing massive forces through precise mechanical control. Every train system in the world balances 4 fundamental forces: traction, the grip between wheel and rail; braking, controlled deceleration; suspension, isolating passengers from track irregularities; and power distribution, getting electricity where it needs to go at the exact moment it's needed. Think of it like a 400-ton ballet. Every component must move in perfect synchronization. The wheels must grip without slipping. The brakes must slow without skidding. The suspension must absorb without bouncing. And the power system must deliver without surging. There's no magic involved, just physics applied with surgical precision. But that's what makes it so fascinating. The real engineering challenge isn't making trains move, it's making them stop, turn, and keep passengers comfortable while doing it. But that leads to the real question. How does a train actually grip the rails when steel wheels on steel tracks should just slip endlessly? You've probably heard people say, trains work like cars, but on rails. That explanation is completely wrong. Cars rely on rubber tires with large contact patches and significant friction. Trains use an entirely different principle. Trains actually use controlled wheel slip. The wheels slide microscopically with each rotation, creating just enough friction without losing control. This is counterintuitive, but it's the secret to rail traction. The contact patch between wheel and rail is smaller than a coin, yet it transfers thousands of pounds of force through this tiny area. To enhance this grip, modern trains use computer-controlled sanders that drop precisely calculated amounts of sand between wheel and rail. Too little sand, and the wheels slip. Too much, and the wheels can't roll properly. The amount varies based on weather conditions, track gradient, and even the time of day as temperature changes affect metal expansion. Inside the locomotive, traction control systems monitor wheel rotation 1,000 times per second, adjusting power delivery to prevent excessive slipping. These systems can detect a wheel slipping by less than a millimeter and immediately reduce power to that specific axle while maintaining full power to others. This happens faster than human perception. You never feel it as a passenger. So why do trains lean into curves instead of staying upright like cars? This is where the engineering gets truly sophisticated. Modern high-speed trains employ banking, or tilting, systems that actively shift the entire passenger compartment up to 8 degrees during turns. Passengers experience this as a gentle lean, similar to what you'd feel in an airplane banking for a turn. But the engineering behind this simple motion involves hydraulic actuators, gyroscopic sensors, and real-time calculations performed by onboard computers. Without banking, passengers would feel crushing lateral forces that could cause injury or severe discomfort at high speeds. The system must predict curves 2 to 3 kilometers ahead and begin tilting gradually to avoid motion sickness. Too rapid a tilt and passengers get nauseous. Too slow, and they feel the lateral forces. Each curve on the track has its own unique tilt profile programmed into the train's computer. What's more remarkable is that this entire process happens while the train remains perfectly centered on the track. Unlike a motorcycle leaning into a turn, the train's wheels stay firmly planted on the rails. Only the passenger compartment moves. It's engineering that works so well, you don't even notice it's happening. Train braking isn't just pressing a pedal. It's orchestrating multiple systems simultaneously in a precisely timed sequence. The primary system on modern electric trains is regenerative braking, which converts the train's momentum back into electricity, feeding power back to the grid. This isn't just environmentally friendly, it's a masterpiece of energy conversion. Up to 80% of the energy used to accelerate the train can be recovered during deceleration. Air brakes provide backup stopping power through compressed air systems that run the length of the entire train. These systems are designed to be fail-safe. If the air pressure drops, the brakes automatically apply. This is why you sometimes hear hissing noises when a train is stopped at a station. That's the sound of the air brake system maintaining pressure. As a final emergency measure, magnetic track brakes can clamp directly onto the rails, creating friction independent of the wheels. These are only used in emergency situations because they create tremendous heat and wear on both the brakes and the track. Coordinating all these systems is a computer that calculates optimal braking force for each car based on passenger load, weather conditions, and track gradient. The braking force applied to the first car might be completely different from the force applied to the last car, all to ensure the train decelerates smoothly without jerking passengers around. A high-speed train traveling at 300 kilometers per hour needs 3 to 4 kilometers to stop safely. That's longer than most airport runways. The braking sequence begins miles before the train actually needs to stop, gradually applying more force as the train approaches its destination. Every time you step onto a train platform and watch that massive machine glide to a perfect stop, it feels like effortless precision. The doors align exactly with the platform markings. The schedule is maintained to the minute. The ride is smooth enough that you can walk the aisles without holding on to anything. But trains aren't defying physics. They're using physics with a level of sophistication that took 200 years to develop. Every time you hear that distinctive hum of electric motors or feel the gentle sway as the train navigates a curve, you're experiencing the culmination of countless engineering refinements. To me, that's the real beauty of rail transportation. Not the speed or the comfort, but the invisible complexity that makes it all look simple. Thousands of components working in harmony to create an experience so seamless that most passengers never give it a second thought. Not magic, but engineering so refined it might as well be. And that's what fascinates me about trains. They're one of the few places where the theoretical meets the practical on such a massive scale, where physics textbooks come to life in the form of machines that move millions of people every day. And now I'm curious, have you ever wondered why some trains can lean into curves while others can't? The answer involves some of the most advanced mechanical engineering on the planet. Check it out now.